Okay, Assalamualaikum warahmatullahi wabarakatuh. Right, so we're going to continue with the new topics on DC-DC converters. We have discussed on the rectifier, AC to DC, and now we have a DC-DC converters. Okay, this is the session's outcomes, which is after completing this session, the students shall be able to. Okay, by the name, by the way, DC-DC converters also known as a DC choppers, and you chop the input voltage, right? So that's why it's known as a DC choppers. Okay, so the session outcome first will be describe the operation of DC choppers. Number two is derive the quantities related to the performance of DC choppers. So we're going to look at, because this is the DC, the output is DC, so we're going to look into the average output voltage, V out, and we're going to get a steady state equation, right, for output voltage. Number three, solve problems related to DC choppers, and finally simulate DC chopper circuit using DC. Okay, let's go straight to the note. Right, so DC-DC converters. A bit of introduction. The main function of DC-DC converter, DC chopper, is to convert a fixed voltage DC source into a variable voltage DC source. And there will be three types of DC chopper will be studied. So we can think of in the situation whereby the only available source is in terms of DC, which is, you can think about the battery if you like. So you have a battery, and then the load requires a different level of, we have a series of loads, right? And this load requires a different level of output voltage, DC voltage. So therefore you need to have a proper DC-DC converters to be able for you to provide the load with the proper required level of voltage. Yes, we do have this voltage regulator, whereby you have this small IC, isn't it, with a 12 volt input, and then you have a 5 volt output, but that only can handle a small amount of current, which is a very low application. Yeah? But in the case of high power applications, we need to have a proper DC-DC converters, which will convert the level of DC from the input to the output will be a different level of DC-DC voltage. Because nowadays we have this electric car, for example, right? Electric car. So this the input can be a series of battery, and then the output can be the audio system, example, isn't it? So they need a proper DC motor of the car, for example. So you need a proper DC-DC converters. Okay, so there are three types of DC choppers or DC-DC converters that we're going to study in EPO 510, whereby in the real world there are many types of DC-DC converters, right? Synchronous buck converters. You can have the metric converter. You can have a resonant converter. There are many types of DC-DC converters available now, but for EPO 510, we only focus on three basic circuit of a DC-DC converters, which is the buck converter or step-down converter, boost converter, the step-up converter, and finally we have one circuit that can function as a step-down and step-up, which is known as a buck boost converter. Okay, so three circuits that we're going to study, and let's look at the first the converter, which is a buck converter, and this very much the circuit connection. We have a input voltage V in, okay, and then this is a chopper switch. Okay, for the switch we can only have a controllable switch to be utilized here. You cannot use the thyristor, of course you cannot use the diode, right? So you must use the controllable switches, and a preferable high frequency switch, which probably you can have a MOSFET, Igbt if you like. All right, and then we have a free commutating diode or we call it as a freewheeling diode, and this must be a very high frequency diode. You cannot use a 50 Hz diode in this circuit, so you must have a very high frequency diode. And then we have this LC. L is the inductor, which is this is also important components in your circuit, the L. so there will be a current through the inductor, as well as there will be a voltage drop across the inductor. And then finally you have the capacitor, which is mainly the used for the filter of the output voltage. Right, so we have a L as a filter to your inductor current, and also C as a filter to your output voltage. Okay, so we have a capacitor here, and finally your R. R is only the resistance which represent the load. The size of R depends on the size of the output, the power of the output. Okay, and we have the output voltage, and in to describe the circuit operation, we have to use this assumption. We need to make some assumption. The first one is, of course, and again in EPO 510, we only going to consider continuous current mode operation. Right, we're going to consider the continuous current mode operation of this IL. Okay, we're going to look at the IL, inductor current, and we only need to consider the continuous mode of this inductor current. Why? I'm going to show you later on why we have to consider that. Okay, and it's continuous, and then a steady state analysis, which means we only we're going to derive the steady state equation by using performing the steady state analysis, which means you can, if you think about the circuit now, if you start from the beginning, it will experience the we call this as transient states, and then at the end when it reaches into steady state, so the value is not changed very much, isn't it? So it reach a steady state. So in that particular steady state, then we do the analysis, not at during the transient of the circuit. Okay, right, and number 3 is the assumption is the capacitor is very, very large, right? Because capacitor will determine the ripple of the output voltage. Remember, the ideal output voltage, the ideal DC voltage is actually a constant current with no with ripple free voltage, isn't it? So this is what we're going to consider. We're going to have a C capacitor, very, very large, and we have a constant output voltage V out, as well as the current through the resistor is also a constant current. And for the buck converter, of course, V out will always lower than V in. So we must have that in mind before we can describe the circuit. Okay, so this is circuit connection, and the size of L and C will can be determined. Later on, I'm going to show you how to get that L and C properly. Okay, so first, right now we're going to look into the circuit operation. Continuous inductor current operation, as what we did assumption just now. We only consider the continuous inductor current operations because there will be a different equation for the output between continuous inductor current operation and discontinuous inductor current operations. And we can actually limit, we can actually protect, we can actually design the circuit to work under continuous inductor current operation, so that we can have one equation. Okay, one equation. And because we have to remember that the output voltage actually need to be regulated, right? So if you have a different equation, then I mean you have to be more clever in controlling or in regulating closed loop design of the circuit. Right, so let's assume that we have a continuous inductor current operation, and if you look at the waveform, this is the continuous current operation. So this is IL, the inductor current. So it is said to be continuous because if you look at the current, okay, if you look at the current, it doesn't touch zero level and there is no intermittent. Okay, so here we have a 0.3 and the maximum can be from 0.47 something. All right, so there is no intermittent. Remember, we deal with a rectifier, and there is an assignment for you. At a rectifier, there is a intermittent, isn't it? Whereby the current goes to the voltage goes to 0, and then you have it stays at 0, Okay, zero level, zero current. Okay, so this is intermittent, right? But now when we have a continuous current, there is no intermittent. Okay, all right. So if you talk about discontinuous, this will happen if you look at the current IL, so you will see this sort of current rise, and then current falls, and then it will stay at zero, and then will rise again. Okay, so in this case, this is known as discontinuous current operation, and V out will no longer equals to V out continuous. Okay, discontinuous is no longer equals to continuous. All right, so let's have this circuit waveform. Okay, and the other thing is we have this duty ratio. All right, duty ratio. I'm going to show you this duty ratio is which mean how long we have this parameter or variable called a duty ratio, and is normally there's a D. Okay, so duty ratio actually determine how long the switch is on. So it is a ratio between T on plus T. T is the period of the switch, equals to 1 over Fs, right? So so it depends on the switching frequency. T equals to 1 over Fs, right? And duty ratio is how long. Duty ratio is T on. So you're going to look into how long this switch is on. This is T on, and this is switch is off. Okay, so T on over T. So this is duty ratio, and we can have D from 0, which is T on equals to 0, and D equals to 1, whereby T on equals to T. Isn't it? Which means you turn on all the time the switch. Isn't it? T on equals to T on equals to 0. So the value can be from, it can be in from 0 to 1, or it can be represented in terms of percentage, the 100%. Okay, or it can be from 0 to 360 degree. In simulation, this is percentage. In simulation, we're going to use this degree. Normally, we're going to use define it as a degree. So which means if you have 0.5, duty ratio is 0.5, so that also equals to duty ratio of 180 degrees, right? D equals to 0.25, sorry, 0.25, 0.25, which is D equals to 90 degrees. Right? So this is duty ratio. Okay, so now we're going to look into the circuit again and consider the turn on and turn off of the switch. Okay, I think I'm going to sketch here the circuit just now so that we can refer properly. So just now we have this, right? Input voltage, and then we have this switch, and then we have the diode, freewheeling diode, and then we have the inductor, capacitor, and we have this resistor. So here you have I in. Okay, so again, notation, right? In terms of notation, the capital letters should be the average value. Okay, capital letter is the average value. So if you talk about I naught, this is the average output voltage. IL is the average of the inductor voltage. Inductor current, sorry, current. So I naught is the average current. IL is the average current of the inductor. Okay, all right, so now we're going to consider the when the switch is on. Okay, so let's talk about when the switch is on. So this is where the switch is, the region where the switch is on. Right, so we're going to look at the what happens to the circuit during turn on of the switch. Okay, so when the switch is on, so it will appear as a short circuit, isn't it? Okay, so the switch will be appear as a short circuit, and therefore this point will be connected to that point, and therefore you're going to see that this diode will be reverse biased, isn't it? It will be reverse biased by the input voltage. So this is your V in. Therefore, it will appear as a open circuit, and now current will flow into the inductor. So you have VL here, plus minus, and you have V out across the R here, isn't it? Okay, so therefore, if now we're going to look into the what happens in this VL. So when the switch is on, we're going to see that there is a voltage of V in. If I can write the equation, so I'm going to have minus V in plus VL. I'm going to write a small letter, sorry, plus V out equals to 0. So VL equals to V in minus V out, isn't it? So there will be, and we know that V out is lower than V in. V in greater than V out. So here we have a positive voltage across your inductor, isn't it? Okay. So there will be a positive voltage across inductor, and this positive voltage inductor will cause the current to linearly increase, linearly rise from IL min, okay, to the IL max, the maximum inductor current. Okay, you get it? Right? So during the switch is on, there will be a voltage, positive voltage of V in minus V out, which will be impressed across inductor, okay, causing the current to linearly rise from IL min to IL max. Alright? Okay, so therefore we can have a, you can read again here, when transistor is turned on for a time t on, the diode is reverse biased, and a voltage of V in minus V out is impressed across the inductor, causing a linear rise in inductor current. Then voltage across inductor become VL equals to V in minus V out, and then we have this equation again, L DIL V in minus V out, and then you integrate the inductor from minimum current IL min to IL max, and on the right hand side we're going to have 0 to T on. So this is the starting of the integral. So we have 0 to T on, isn't it? So you get 0 to T on dt, and you solve this, you have IL max minus IL min equals to V in T on over L. And if you look at the circuit again, this also equals to delta IL, okay, delta L, which is the ripple of the inductor current. Right, so this is the ripple of the inductor current. So this is equation 1, right? So during turn on, and now we're going to look at when the switch is off. So I'm going to write again the circuit. I'm going to write it here. So you have again positive, negative, the switch. Just put it as a BJT if you like, no worries. BJT MOSFET. And then we have this inductor, capacitor. Okay, so during turn off of the transistor, or the switch, we're going to see that this will be open circuit, isn't it? It will appear as an open circuit, and current cannot change or cannot drop to zero instantaneously because you still have a constant inductor still stored an energy, so current must flow in the inductor. Therefore, it will force the diode to turn on, right? So now you're going to have this circuit operation, isn't it? Okay, so you only see this at the out. During turn off, you're going to see that the diode will be turned on, so it will appear as a short circuit here, and current will flow this in the same direction, and you have this is also I L. So in this case, you're going to have plus minus VL again, and we only have plus minus V out, isn't it? So if you do the KVL, you're going to have plus VL plus V out equals to 0, and therefore VL equals to minus V out. So there will be a negative voltage across the inductor, as you seen here. So you can look at this. This is a negative voltage. So this is VL, voltage constant. So this is actually V out, right? Negative. Okay. So there is a negative voltage across your inductor, causing the current to linearly fall. So instead of rise, because of negative voltage, now the current reduce or falls from IL max to IL min. Okay, from IL max to IL min. Right, during turn off. This is your off. Okay, so that is the circuit operation, and we look into the derivation of equation. When the transistor is turned off, for time t off, the inductor current is diverted through freewheeling diode. So turn on the freewheeling diode. A reverse voltage V out is then impressed across the inductor, causing a linear decrease or linear fall in current, and inductor voltage becomes, so we have VL equals to V out, and then you do this L DIL over dt minus V out. And again, now look at the limit. Now it has to be from IL max to IL min, isn't it? Because you are dropped, okay, reduce or falls from IL max to IL min, right? So you start with IL max, so that's why you have a we call it lower limit with IL max, and the upper limit should be the IL min, right? And also to the for the voltage, it has to be from T on to T, isn't it? So we know that this is T on, because from 0 we have this current rise from 0 to T on, and this is T, isn't it? Rise again. So the limit is from T on and to T, right? So that's why you have this integration of the limit. Right, so you do the same, you solve for this DIL, then you get the IL min minus IL max minus V out T minus T on L, and finally you find out that equation number 2, IL max equals to IL min, and this also the delta to be we're going to equate equation 1 equation 2, so you have to have IL max minus IL min, and again this also delta IL, isn't it? Right, so now we equate both equations. Equation 2 equals to 1, therefore V in minus 1, and finally you found out that the output voltage, the average of the output voltage, can be described by this equation. V out equals to D multiplied by V in, and we know that D can be from it's already here. Okay, so D can be from 0 to 1, or it can be 0% to 100%, or in terms of PCM later on, percent, from 0 degree to 360 degree. Okay, it can be represented any of these parameter. Okay, so here from 0 to 1, and therefore if you look at this equation, so very much V out depends on the value of D, isn't it? Okay, so the low voltage V out can be controlled by varying the duty cycle D, but cannot be larger than input voltage. Of course, the voltage conversion ratio depends solely on duty ratio and is dependent of load condition. This is actually to explain or to differentiate between voltage equation for continuous operation with V out with discontinuous operation. Okay, so if you further your study in to master's degree by top course, normally we're going to look into this mode V out to describe the output voltage during the discontinuous of inductor current. And if you look at the V out, then it is actually depend on the load conditions. For discontinuous, the equation will depends on the load condition, which is R, R and the, I can't remember. Okay, so for EPO 510, we only focus on the V out continuous. Right? Next. Okay, so we're going to look into the boundary between continuous and discontinuous current. Before I continue with that, I'm going to show you the simulation and to show you what is a continuous and the difference between continuous and discontinuous. Right, so I'm going to put it somewhere here, and it's going to be my circuit, right? And on the left hand side here is actually showing you the switch voltage, okay, the pass to your switch, and then the inductor current as well as the VL. Okay, so don't worry, I already put in the Padlet, so please you have to help yourself download and try to simulate the circuit. Okay, so but I'm going to show you a few things. One is that now you have a Igbt, okay, and we're going to use this gating block. So we have a frequency of 2000, okay, the frequency is 2000 hertz, and number of point is 0, so that you can have from 0 to 270. Then you have 360 degrees here, 0, 270 degree, and this is, so what does it mean? What is the duty ratio now? We know that duty ratio 1 equals to 360 degrees, right? So therefore, if you have 270 degree, therefore your duty ratio equals to D equals to 270 degree divided by 360 degree. So that gives you what? 0. Sorry, to calculate. Okay, so we have this got it. So we have D equals to 270 degree divided by 360 degrees, so that gives me 0.75, isn't it? Yeah? So the duty ratio is 0.75. So we're going to look at it. So you need to change here. If you want to have 0.5, it will be 180 degree, isn't it? Okay, so you have to change here to get a different duty ratio. Okay, next, what else? The inductor size is 500 microhenry, 1500, and the load is R equals to 2 ohm. And now look into the simulation parameter. Remember, you have 2 kilohertz. Your frequency now Fs equals to 2000, right? So therefore, Tf S equals to 1 over 2000. So that will be equals to what? Okay, so you think about the Fs equals to 2000, and Ts will be 1 over 2000, then it equals to 0.5 millisecond, right? 0.5 milliseconds. So this switching frequency is 0.5. I mean the period is 0.5 milliseconds. So you have to be careful with the simulation. So you need to have a because time step, isn't it? Time step small enough so that you get a proper square wave. If not, you're going to have, for example, not really a square wave. If you make a t-step, the simulation step very large, then you're not going to have a proper on and off. Okay, instead of we have a step, I mean a square shape on, now you have a not square shape. So that will affect the output of the simulation. Okay, so in this case, now my time step equals to 1 microseconds. Remember, it has to be, the rule of thumb is it will be 1% of the TS, isn't it? Okay, so now I'm going to just now we have 0.5 millisecond, and now I choose my time step have to be 1 microsecond, right? And then total time is 0.2, so that I will allow the circuit to get into its steady state. If I run very short times, then most probably the circuit is still climb the ladder, okay, and then you stop the simulation, so you will not get a proper output or the circuit waveform. Okay, and we'll print time 0.198 so that I can display 4 cycles. All right, so let's simulate this on simulation, and now you get this switch. This is a pulse to your switch, turn on, turn off. Okay, so we have turn on, turn off again, and then the switching period is 0.5 millisecond. Look at that, 0.5. So you have 1, 2, 3, 0.5 millisecond. And then we know that during turn on, the current will rise because there is a positive voltage of V in minus V out across your inductor, and therefore causing the current to rise. And then we have this output voltage, negative output voltage impressed across the inductor, causing the current to reduce from IL max to IL min. So this is VL, the voltage across your inductor. It's a straight line because it's a V in minus V out. And during turn on, turn off, you have output voltage equals to minus V out. Okay, right. So I'm going to show you what happens if the circuit goes into its discontinuous operation. And in order to do that, I'm going to increase the resistance, for example, to 100 ohm. And therefore, if you talk about the current, it will be reduced, isn't it? If you have the same output voltage, if you increase the value of R, therefore the current will reduce, right? So I'm going to simulate it again. Look at the output inductor current. Now, if you look at the inductor current, there is a intermittent, isn't it? So the circuit is already into discontinuous operation. So this is discontinuous inductor current operation. And I must show you the output voltage as well, isn't it? I'm going to add another output voltage. I'm going to add another screen which shows the output voltage. Okay, so just now, can I change that back to 2 ohm? Okay, I'm going to change back to 2 ohm. run again circuit. Okay, so now we have a continuous operation, isn't it? So this is a continuous operation, therefore we can estimate, we can predict the output voltage, because V out equals to D multiplied by V in. Just now we know that D equals to 0.75, and then you multiply by 48. Okay, that will give, okay, so if you multiply again, so V out equals to 0.75 multiplied by 48, then you get 36 volt. So look at this. So this is a ripple, small ripple there, and if I can do the measurement, take the average, it will give me the value of 36 volt. And this is correspond to the derivation of the equation that we have just now, the continuous output voltage. During the continuous inductor current, the output voltage equals to D multiplied by V in. Okay, so now I just show you just now the discontinuous operation. I'm going to increase that to 100 ohm, and then look at the current again. Okay, the current is discontinuous, and look at the value of V out. It is 46, isn't it? So it's no longer follow D equals to V out. It's no longer D multiplied by V in. In fact, it's a very higher compared to the continuous operation, isn't it? So there will be a different equation actually. During master's program, then you'll be able to analyze the circuit with the discontinuous operations, and it will be different equation. Okay, so for EPO 510, we only consider V out equals to dV in, or continuous inductor current operation. But we must know the boundary. Okay, the boundary between continuous and discontinuous. So in this case, we're going to determine what are the elements, what are the components of the buck converter here that will determine the boundary between continuous and discontinuous. Remember, the continuous is whereby the current goes from there, isn't it? So it continues all the time, doesn't have this discontinuous, and therefore if you want to find the boundary, it is actually whereby the current touches the zero level. For example, you have rise to the IL max, and then it touches zero levels here, and then it rise again. See it? So this is actually the boundary between continuous and discontinuous operation. It is important to determine this because you can actually design the circuit so that it won't fall into the discontinuous operation. So you protect your circuit so that it doesn't work under discontinuous operation. So we're going to determine what will be the components of the, just now I changed this, isn't it? So R is actually, or the output current is one of the variable parameters that determine the boundary of the between continuous and discontinuous. And actually there is another one, which is the inductor. The size of inductor also determine the boundary between continuous and discontinuous. So we're going to look at these two, how to design that so that we get the boundary condition. Okay, so feel free to download the circuit and simulate and explore yourself. All right, I cannot show everything during the lecture, so you have to explore, you have to motivate yourself to explore the circuits, test a new, just change everything, but you must know what did you change so the circuit be different, isn't it? So use the PC. It's very, very good for powertronics simulation. Okay, so now I'm going coming back to the note. Okay, so let's go back to the The function of low pass filter is to filter out any. Okay. Boundary between continuous and discontinuous current. The term continuous and discontinuous refer to the inductor current. Yes, I did show you just now. Continuous means the inductor continuously flow with positive value, and in discontinuous mode, the current goes to zero and stay at the zero level until the end of the period. Intermittent condition of the current. So in this case, the average current I naught equals to the average inductor. So we know that for only for the buck converter, if I can just show you the output side, we have this inductor current, inductor, then we have this capacitor, and we have this resistor. So in here we're going to have, this is your IL, this is your I naught, because I naught is always a constant current, because we have a very large capacitor, our assumption is. So if you look at the scope, oscilloscope, you're going to see a straight line of I naught as well as V naught. There's a straight line, constant output current and voltage. And but for IL, we know just now it is sawtooth, isn't it? If I can show you the axis, it is sawtooth. Okay, so the average of this current, if I take the average of IL, so this also the equals to the output current, isn't it? So this is also the output current, equals to the output current, and what left is there will be a ripple current that flows through your capacitor here. Why? Because at this point, if you look at this point, IL equals to IC plus I naught 3, and IC equals to I naught minus IL. Right? So there is a constant current at the output, and minus this IL, we have this ripple current. So that ripple will be pushed into your capacitor here. Is that it? So it remove. Okay, so you have this is your inductor current. It remove the ripple, leave the average through the output, and therefore if you look at the current at the capacitor, there will be a ripple current. Okay, all right. What else? So there is a I naught equals to IL. So now we have the average of I naught also equals to IL. And if you look at this IL, it is actually the average. So the average will actually equal IL max plus IL min divided by 2. So this is the average value. The average of the inductor current IL. And therefore you have IL max plus IL min equals to 2 I naught. But during critical condition, during the boundary condition, we know that the current touches the zero level, isn't it? Which means IL min equals to 0, and you still have that IL max there. Isn't it? So your minimum inductor current actually equals to 0. So therefore you have this term which is IL min equals to 0. Therefore you have IL max equals to 2I naught. That equation. IL max equals to 2I naught. Right. Therefore, at the boundary, the average output current. So if you talk about the inductor critical current, at the boundary, the average output current I naught critical becomes that. I naught critical. So this is the critical condition. I naught equals to IL max divided by 2. This is from the above equation just now. From equation 1, where is it? Go back to equation 1. Alright, so from this equation, right, from this equation, IM max minus IM min, V in minus V out over T on, and we know that now IM min equals to 0. So we're going to have this equation at the output, and finally you find out that this equation. So you just use equation 1 just now, as well as this equation, put into equation 1, and finally you found out that I not critical, the minimum size of the output actually will determine the boundary. So you can find the minimum current I not critical equals to V in minus V out T on over T L. So what does it mean? So if you actually if you buy or if you just use a DC-DC converter, buck converter, where it's already come with the, where is it? So you buy a DC-DC buck converter, and then you already know that the circuit has this, the size of inductor is already there, it's already been designed, so you just use that buck converter, and just for just now we have in the PC, which is, if I'm not mistaken, is 0.5 millihenry, isn't it? It is 0.5 millihenry here. Then we have a capacitor, and we have this R. We don't know. Okay, so that means with this circuit, and if you operate with a certain frequency and duty ratio, because that we know that T equals to T on over T, and we know that T on equals to D multiplied by T. So if you operate a certain duty ratio with a certain frequency, and we know the size of L as well as V in and V out, then you will know, you can you will actually calculate, you can calculate what is the minimum size of the output current that you can apply to your DC-DC converter here. Or else, if you have the output current which is lower than I not critical, you will force the circuit to be in the discontinuous inductor current. Okay, so this is very important in design process. So so just now, and that's why when I change the R, remember V out is constant. Okay, V out is constant value, V equals to IR, isn't it? So I equals to V over R. So V is fixed, so if I increase, V is fixed. When I increase R, then I will reduce, isn't it? So when I change just now until 100 ohm, then we see that the current actually has go below the I not critical of the circuit. So that's why we see that the output inductor current become discontinuous, and the output voltage is higher than the V out. We expect the V out of 36 volt in the simulation just now, isn't it? Okay, so this is a user perspective, and if you are a designer, if you think about the designer perspective, if you are the designer, you are an engineer, you're going to develop the buck boost converter, so you need to consider the size of critical L critical here, isn't it? So you need to find, so your customer, or there will be a specification given to you which states what is the size of output or the load current. So you are specified with this I naught, and we know that you're going to operate at a certain frequency as well as the duty ratio. Then you can see the size, you can determine the size of L, the minimum size of L. so that the converter is still in the continuous current mode operation. So you just actually modify this equation. So you make the L as a title of the equation, and you change with the value I naught. Therefore, that become L critical. This become I naught. Right? So you have two perspectives here. So you can know what is an L critical in design process, and if you buy the DC-DC converter from the internet, for example, then you will know what is the current that you can apply to the converter before it goes into discontinuous mode current operation. Right? So the above equation shows that from the user perspective, if the output DC current drops below I not critical, the inductor current becomes discontinuous, while from the designer perspective, if L used is lower than L critical, the inductor current also becomes discontinuous. Right? So let's look at the example again. Okay, if I can. Okay, so now we look back to the PSIM just now, the simulation just now, whereby you have this input voltage of 48, and we know that from the gate signals here, we know that the D equals to 0.75, the frequency is 2 kilohertz, and the inductor is 5 microhenry, and the capacitor is 1500 or 1.5 millihenries here. And now we need to determine the inductor current as well as the R here, so that we can do the simulation. So that we're going to look at the simulate the case of boundary conditions, isn't it? So use the mathcat here, right? So V in, you just type V in. So how to do that? Just V, and if you want to make it a subscript, you just hit the dot button. Okay, the dot button, so it become the subscript, and then you can put this I in, and then just if you want to assign a value, then or you want to write an equation, just write a normal equal sign, and then you just this is already there, put X here, then you assign or you write an equations. Okay, and then what else? So subscript, you just hit the dot button, and then if you want to have the superscript, for example, to the temp of -6, so you need to use the symbol here. You can have a number 6, button 6, which is the head button. Okay, so if you want to get this superscript, you must hit this head button, so it become -6 superscript, and then you just put it -6 to get the 10 to the power of -6, and then you define frequency 2000 kilohertz. It's very good to have a mathcat, right? Rather than the yes, you can also use an Excel, but for mathcat you can see the equations and how it's solve it. So TS equals to 1 over Fs, will become 0.5 millisecond. T on, D multiplied by TS, so it become 3.75, 0.375 millisecond. And then from the note just now, I critical equals to V in minus V out. So we know that V out equals to 6 multiplied by T on. So the minimum current, output current is 4.5 amps. So you need to determine the load resistor in order for you to do the simulation. We know that the output is 36 volts. So therefore you divide by I not critical, then it gives you 8 ohm. So if I change the resistor, the output resistor with 8 ohm, then we can see the boundary of the inductor between continuous and discontinuous. So let's do that. Going to change that to 8 ohm, and then run the circuit again. Now you can see this. Look at that. Okay, exactly at 0 level. It touches 0 and then it rises again. So this is the boundary between continuous and discontinuous inductor current operation, right? So in this case, if I increase the resistor, which means the output current is smaller than the boundary condition. For example, I put it as a 15 ohm. Now the current is reduced below the I not critical. If I run the summation again, now there is become discontinuous. It become discontinuous now, right? So that's very much what is the boundary topic, right? And then ripple current from equation 1, 2, 3, 4. So look back at the ripple current, then you can determine the IL, delta IL. Okay, you can calculate also delta IL max minus I min, so that gives you back the equation. So this is straightforward. Okay, just to look at the ripple of the inductor current. Now we're going to look on the output ripple voltage. Okay, for the output ripple voltage, you need to understand the current of the capacitor. So just now I did mention to you, at the output side you're going to have, this is your inductor, capacitor, and your output, isn't it? And we know that you have a IL there, and then you have a constant output current I0, and we have a ripple current IC here. Why? Because at this particular node, we know that IL equals to, I need to write proper, IL equals to IC plus I0, isn't it? Yeah, I equals to IC plus I0. So we know that this is with the ripple, continuous current operation, and then the average of that also equals to IL also equals to I0, isn't it? So therefore IC equals to I0 minus IL. So I0 minus IL. So you're going to get your IC. Okay. So I0, the constant current, the average, minus the ripple. So you're going to get these values, the waveform, isn't it? Going to that waveform in the current, IC current. So when you look further on the waveform, during this, this is your capacitor current. During this time, the output voltage also equals to capacitor voltage VC, isn't it? Okay, V out equals to VC, right? So if you look for the V out or VC, you're going to see that when the current IL equals to I0, you're going to see that it reached the minimum. And again, at this point, you're going to see that the output current reach its maximum, isn't it? So this is also known the output voltage ripple, peak to peak. And normally, the output voltage is limited to 5%, 2%, 5% of the average value. Okay, so given any average value, so the ripple of the voltage must be about 2% to 5%. Yes, limit. You cannot go very large ripple, right? It's not good. Okay, so in order for you to get that delta V naught, now we're going to apply this equation. We know that the input capacitor current equals to C dVC over dt, isn't it? And that also gives you C dV naught over dt. And we also know that dV naught is also can be represented by this ripple, delta V, isn't it? Right? And therefore, you're going to see that delta V naught equals to 1 over C. So you cross multiply 1 over C, and you integrate current with respect to dt. So you just simply actually cross multiply, and then you get this I over C. So this is very much okay. So this is very much the area under the capacitor current, isn't it? The integration is always the area under the curve. So if you look carefully, it is actually the triangle. If you want to integrate from that point to that point, it's just actually the area under the capacitor current, which is the triangle area. So 1 over C, half multiplied by height multiplied by base. So the height is delta IL over 2. So we always know that this is the half or the average between IL max and IL min, and that one is IL, and that will give you delta IL over 2. So therefore you get this delta IL, and this is always T over 2. Okay, half of the period. It is always half of the period. So now it becomes delta IL multiplied by T 8C. So what is delta IL? You can use this equation. Okay, so you know what is delta IL from this equation. Then you can determine actually the delta V naught. Okay, the size of the ripple given the capacitor, the value of capacitor, or either way, or you can choose, or you can design the capacitor size given any percentage of the ripple, delta V naught. Right? For example, we come back to this example here. Where is it? Okay, so let's look back on the PCM simulation just now. Now I'm going to remove the value of capacitor. So we're going to find what is the size of capacitor, so that, look at this example, capacitor value of ripple is 2% of the output voltage. So the design says that you must have the ripple which is only 2% of the average output voltage. So we know that the average output voltage is 36, right? And we are given that you must limit that 2%. So therefore delta V naught equals to 0.02, which is 2% of V out 36, and that gives me 0.72 volt, which means if you measure later on, the peak to peak of the output voltage only limited to 0.72 volt. Right. So first, if you look at the equation just now, before you can calculate the size of capacitor here, so you need to change the title of this equation. So it becomes C equals delta I naught LT over delta V naught 8, isn't it? So before that, you need to find delta IL. So this is your delta IL. So I'm going to already calculate here. Delta IL equals to V naught 1 minus D over L multiplied by TS. That gives me 9 amps. So the delta IL is 9 amps. And finally, I can calculate the capacitor here. Okay, can calculate the capacitor here by using the math cat, or you can use your calculator if you like. So delta IL TS divided by 8 delta V naught, that gives me 7.813 to the power of 10 minus 4, or this is actually it is 0.7813 micro millisecond, millifarad. Okay, 0.7813. So I'm going to put that into my simulation again. Remember, this is the original simulation circuit, 2 ohm with 500 microhenry. So I'm going to click and change that to 0.7813 to the power of millifarad, isn't it? So it's enough for me to give to put amp, to inform the PCM it is a millifarad. Okay, 7.8. So they give me 0.15 millifarad. Then run the circuit again, and that gave me this form. So it is still continuous, isn't it? It is continuous condition. Now we're going to measure from peak two peak, maximum peak, minimum peak of the output voltage, and this must have 0 point at least or else about approximately 0.72 volt. Okay, so how to measure that? You use this button, click this. Okay, so actually you must have put somewhere here, click on the V0 waveform and then click the maximum, so that will give me V out 3.64. so highlight this and right click, send to calculator, so it will send directly to first value here. Then I'm going to look at the minimum, so this is the minimum value, right click again, send to calculator. So now to get the difference between the two values here, I click that one, use minus button, click another one there and equal sign, so that gives me 0.73, right? So very much I mean close to 0.72 the actual, which is 0.72, but in PCM of course there is some probably because of the time step it's not small enough, right? But it's acceptable, and it's acceptable if you have 0.73 volt. Okay, so which means by using all the equations here you can actually properly design your circuit, right? You can properly design your circuit. So again, please download final exam questions, right? Final exam question, there's a lot of questions on the DCDC converters, so please do it. Inshallah we can discuss that, right? So the next video will be on boost converter as well as the buck boost converter. Thank you.